Good morning, friends and dear students. I am really very happy that I am in the stage of my last few lectures in flight mechanics. This flight mechanics is the course for 4th semester aeronautical student in the Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have covered all the topics of flight mechanics, especially the aircraft performance topics only I have covered, which covers the first module, Introduction to Flight Mechanics, in which I have discussed about International Standard Atmosphere. I have also discussed about different airspeed, that is true airspeed, indicated airspeed, calibrated airspeed. Also, I have discussed about lift, drag forces, drag polar, generation of the lift, different types of aerofoils, components of the aircraft, thrust required, thrust available, power available. These all things I have covered in my first module. In second module, it is a cruise performance. In the cruise performance, I have discussed about cruising parameters like range, endurance, maximum range, maximum endurance, thrust required, power required, minimum drag velocity. These all things I have covered in my cruise performance. In my climb performance, I have discussed about maximum rate of climb, best climb angle, sink rate, gliding performance, these all things in my module number 3. In module number 4, which this is the topic related to the module number 4. In module number 4, we have the turning flight, that is coordinated turning, which is in the same XY plane. Your aircraft is turning in the same XY plane. It is not going up or down. There is no pitching. Only the rudder and the ailerons are used, no elevators are used. So aircraft is just turning in the same plane. That is called the steady coordinated turn. Another thing is the vertical pull-up. If aircraft is going like this, it is called the vertical pull-up. And if from here, from bottom to the top, it is the pull-up, and from the top to the bottom, it is pull down. So we will be discussing today in this. However, all the derivations and the numericals are already completed. Today, I will take some questions on this topic, that is discussion on question bank solution, that is maneuvering performance. So, here I will be discussing the maneuvering performance. In this, till now we have discussed the non-accelerated flight, but from here onwards, in this module and the next, that is the module number 5, landing and the takeoff performance, we have the accelerated flight, where for every flight there is a change in the direction or there is a change in the velocity, then we say that the condition is accelerated. So, I am Dr. Yagya Dutta Dwivedi, professor from Institute of Aeronautical Engineering, Hyderabad, India, from the Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. In today's topic, I am going to discuss about turn flight maneuver, pull-up maneuver. These are the two main topics. However, in this, we will be having number of subtopics that some of the questions I am going to handle today as per our question bank. First question I will take from our bank is illustrate the turn performance and flight maneuver. These are the two terms here, turn performance and flight maneuver. So, maneuver in literature means every non-simple motion. Means it is not a simple just going like that. You can do like this, like this, like this. Different types of motion if you do, then we can say that it is a non-simple motion. The non-simple motion are known as a maneuver. In aeronautics, maneuver refers to a transfer from a level, constant speed, constant altitude, straight line flight to an accelerated flight, which involves at least one turn rotation. So, in this case, transfer from a lever. If aircraft is flying like this, and if you start turning like this, minimum one circle should be there. Then it is a it is a turn performance, and it is an accelerated flight which involves at least one turn per rotation. Means every rotation you should have minimum one turn. This you can see here that this is the aircraft, and it is x-axis, which is the rolling axis. We have here the pitch axis, it is y, and we have the z-axis, that is the yaw. We have here the rudder. This rudder, the purpose of this rudder is to move the nose left or right. This is the one motion. Yeah, and if you start the elevator, nose will go up and down. This is the right and this is the left. This right and lefts are decided from the pilot. And if you apply ailerons here, up and down, then it will roll with respect to x-axis like this or this. So if this is the aircraft, rolling is moving the wing down and up. This is called the rolling. Any flight operation that includes at least one rotation around one of its three body axes, x, y and z, as shown in this diagram, it is called the maneuver. The rotation about the x-axis is referred to as a roll. So if you are flying the aircraft and you are rotating the aircraft with respect to this axis, that is the x-axis, means your wings are going down like this. It is called the roll. And if in the y-axis, this is the y-axis, so this is the y-axis, so nose going up and down. This is called the pitching, and rotation about the z-axis, nose will go left and the right, it is called a yaw. So we have the three types of rotation. First is the roll, second is the pitch, and third is the yaw. Next question, discuss about turning performance with suitable sketch. So here we have the sketch. So we will see, and this your circle is at the in XY plane. So here if you see bank angle, it is phi. This is the bank angle. Here it is turned from here to here. This is called the bank angle. And your lift is in this direction. It is called the lift. This side we have the L cos of phi, and in this side we have the L sine of phi. And this is your, here you will FC will act. This is the Z direction and this is the Y direction. If you see the rotation in x-axis, it is the psi, and your aircraft is moving from this is the north and you are going towards, this is the west, this is the east, and this is the south. So you are just turning in this way. So this is the simple explanation for turning performance. All the parameters are shown here. X is the velocity direction in the x direction. Now we will discuss how turning maneuver are useful for the fighter airplane, explained with sketch. So here, if you see here, very important, all this turning maneuver or the vertical maneuvers are very much essential for the fighter aircraft, as the fighter aircrafts are designed for a certain maneuvers. Whenever your aircrafts are flying, fighters are used for the war, and the enemy is looking after to hit the aircraft. But if you have very high maneuver, very high turning, you can see in this diagram, your aircraft is here, your missile is started here, and the radar has calculated what is the speed and all. So as per the speed, missile is running, and they expected that either when you reach here, it will be hitting. But due to the high maneuver, your aircraft has reached ahead and your missile has crashed like this. So missile could not hit the aircraft due to high turning maneuver of the fighter plane. So for any fighter plane like Rafale, India has the Rafale aircraft. Rafale has got much maneuverability than any other aircraft like F-16 and all. So India has acquired the Rafale by its maneuvering capability. So this is the explanation for this question. Explain about the centripetal acceleration and the centrifugal force for the airplane performance. So if you see here, the aircraft is having the radius r and it is moving with a velocity v. There will be a centripetal acceleration. This centripetal acceleration will generate a centrifugal force which is in opposite direction. Velocity is in this direction. So if you see here, weight is mg. If it is at the top, then it is a centrifugal force. This centrifugal force and mg will be countering each other, and we know that this is mv square by r, where this r is the radius of the circle. So as and when your aircraft is maneuvering, or it is turning, or it is doing the pull-up, there will be a radius of that. That radius is very important parameter for any aircraft too. And if you see here, if you have the rotation for the International Space Station, this FC and weight are equal, your satellite will be always traveling. So we have to make your aircraft, your space vehicle in such a way, the satellite, that the weight of the satellite and the centrifugal force which is acting are equal, and your aircraft will, your satellite will be always remain in the same circle. Illustrate the load factor and the bank angle. The ratio between the lift L and the aircraft weight W is called the load factor. So L by W is equal to N, that is called the load factor. Important performance parameter and denoted by N. N is equal to L by W. So the load factor indeed is a normalized acceleration and denoted by G in place of N and called the G load. For example, if lift is twice to weight, then known as N is equal to 2, or it is called 2G load. In cruise flight, N is equal to 1, but in turning flight, N is greater than 1. We know that the N is equal to 1 by cos phi. The load factor N is only a function of the bank angle. The maximum permissible load factor is equivalent to the maximum permissible bank angle. The maximum load is limited by structure and the human tolerance. If load factor N is equal to 3 means structure has to bear 3 times load, or 3G, and human also to sustain 3G force, which will affect the blood circulation of the human body. So these are the, so N max is equal to 1 by cos phi max. So this is the basic of the load factor and the bank angle. Bank angle and the load factor both are related. So N is equal to 1 by cos of bank angle. Now discuss about the turn radius of the maneuvering performance. In cruise flight, where lift is equal to weight, the load factor N is equal to 1 means structure to carry and sustain own weight, and pilot and the crew to take its own weight. If aircraft turns 45 degree, then n is equal to 1.41 means 41% more load structure and crew to carry. We know by governing equation that Fc is equal to L sin phi and W is equal to L cos phi. By dividing this equation, we can get L sin phi by L cos phi is equal to Fc by W, or tan phi is equal to Fc is equal to mv square by R, and Rw is already there. So tan phi is equal to mv square by Rw. So this is equal to here v square by here it is mg. So this is cancelled. Here v square by gr. So this we can v square r is equal to ac. That is the centripetal acceleration. Centripetal acceleration AC by g. So this tan phi is equal to centripetal acceleration divided by the gravitational acceleration. Here Fc is equal to mv square r, W is equal to mg, and v square r is equal to AC. Now this AC, if you see here, AC is equal to g tan phi. G tan phi, and here two acceleration, that is g, that is the gravitational acceleration, and AC is the centripetal acceleration, can be added as two vectors. The overall acceleration over the structure and human is A is equal to under root g square plus A square. So here g square plus AC, we can write g sin phi. So here we can take g outside, under root 1 plus tan phi square. So we can further go ahead. Cos square phi plus tan square sin square phi is equal to 1. Then 1 by n square plus, so cos phi is equal to 1 by n whole square plus sin square phi is equal to 1. So sin phi is equal to under root 1 minus 1 by n square. So this 1 we can write n square by n square minus 1 by n square. So 1 by n we have taken outside, it is n square minus 1. So this is equal to 1 by n is equal to cos phi, and it is n square minus 1 is equal to, so we can write that this sin phi by cos phi is equal to tan phi, and tan phi is equal to under root n square minus 1. We know that tan phi also is equal to v square by gr. So this r is equal to v square by g tan phi. So r is equal to v square by g under root n square minus 1, or r is equal to v square by g tan phi. The minimum turn radius can be achieved when 1. The highest possible bank angle, and 2. The lowest possible airspeed. So r is equal to v square minimum by g tan phi. So next question, discuss about load factor parameter for the aircraft performance. So 4 important parameters are described here: maximum producible load factor, corner velocity, maximum of the maximum load factor, airspeed that corresponds to the maximum of the maximum load factor. So maximum producible load factor. So what is the meaning of maximum? That we will discuss in this question. Illustrate the maximum allowable and producible load factor. As the bank angle is increased, the magnitude of the lift should be increased too. So the increased CL is given as CL is equal to 2nw by rho v square. As L increases, the drag due to lift will also increase. So drag is equal to half rho v square s CD. Half rho v square s, for the CD we can write CD naught plus K CL square. This is your drag polar. This we have to put this value. To maintain a sustained level turn, the engine thrust should also be increased. For cruise and the level flight, T is equal to D. So now T is equal to D, half rho v square s. CD naught plus K, and for the CL we will write 2NW by rho V square S whole square. Solving this equation, we get the load factor N is equal to under root rho V square S by 2KW square T minus half rho V square S CD naught. Load factor N is the function of the velocity, engine thrust, altitude, aircraft weight, and aerodynamic features. The maximum value of N is obtained by implying the maximum thrust, having the lowest weight, and flying at the lowest altitude. Maximum load factor N maximum is equal to whole under root rho naught V square S divided by 2K W square minimum. Here we can write T maximum here W minimum, here T maximum minus half rho naught V square S CD naught. So this is the maximum load factor which an aircraft can sustain. So next question is, illustrate the diagram, the variation of the maximum load factor N versus airspeed in a level turn. So very important diagram. This is the maximum producible load factor, that is N maximum, and here is the velocity in this direction. Here if you see, we have here A, then we have here B, this is the B, this is the C, this is the D, here also D. So these are the some points, very important points I have explained here, each and every one. So what is the point A here? Point A is the maximum load factor. Represent the maximum of the maximum load factor. This point corresponds to the velocity at which the highest bank angle can be obtained. So this is the velocity where the maximum or highest bank angle phi can be obtained. Point B here, this point B corresponds to the stall speed with N is equal to 1. So this is the stall speed at N is equal to 1. Point C here, this is the point C, airspeed below which the load factor is constrained by the stall CL max rather than the maximum engine thrust. So this is a point, if you are below this point, your aerodynamic characteristics will constrain, not the structural characteristics. Here is the point D, represents the maximum velocity with load factor 1 here. In this point, aircraft is not able to turn. So in this case, if you are flying here, aircraft will not be able to turn. This is the maximum velocity to the turn. So this point A, B, C and D, very important points that we have to understand each and every point. Question number 10. What is the maximum of the maximum load factor? Show with mathematical expression for this. In level 10, the aircraft drag is equal to the thrust. So we know that N is equal to L by W. We can write T by T. L by W, T is equal to below this T is equal to D. So L by D, L by W, T by D. Now we can change T by W, that is the, and L by D here. So load factor is equivalent to the multiplication of thrust to weight ratio T by W and lift to drag ratio. If the engine thrust remains constant at its maximum, if T is a constant, the producible load factor will reach its absolute maximum value N max max when the aircraft has its maximum lift to drag ratio. So if your thrust remains constant, the wherever you have L by D maximum, that point will produce the maximum to maximum load factor, and max max is equal to T max by W L by D max. The aircraft maximum lift to drag ratio that is L by D max is equal to 1 by 2 under root K CD naught, which we have already done. Putting this value in equation A, we will get N max max here. In place of L by D maximum, we will put 1 by under root 2 K CD naught. So N max max is equal to T max divided by 2W under root K CD naught. So this equation says that for a maximum load factor, thrust should be maximum and L by D should be maximum. So designer to choose more powerful engine with high L by D ratio. What is the airspeed for the maximum of the maximum load factor? Maximum of the maximum load factor. So here we have the equation, the speed is Vn max is equal to under root T max by rho S CD naught. The airspeed that corresponds to the maximum of the maximum load factor is only a function of 4 parameters. These are the altitude, means this rho, then wing area S, rho, then S means area, then zero lift drag coefficient, that is the CD naught, and maximum engine thrust, T maximum. So these 4 parameters are very important to achieve the velocity for load factor maximum. And point A is less than the maximum speed and more than the corner speed. So point A in the previous diagram, in which the less than the maximum speed and more than the corner speed. So what do you understand by the vertical maneuver? Explain with suitable diagram about different positions on vertical maneuver. In level turn, only 2 rotations are considered, that is roll and the yaw. So if you are turning, there are only 2 maneuvers, 2 motions, that is the roll and the yaw. Roll is in the x-axis and yaw in the z-axis. There are another maneuver that are not based on the roll and the yaw and depend upon the pitch motion. That is called the pull up, pull down. So if you want to turn the aircraft, so you have to roll and the turn, means angle phi and the yaw angle. But if you want to make pull up, then you have to use the another control for the pull up or the pull down. Pull down also known as a push over dive, and the pull out from the steep dive fall in this group. So in the vertical maneuver, pull up, pull down, it is also push over dive. Aircraft is just falling down, and pull out from the steep dive. So aircraft is diving and again it is pulling out. These all motions are part of the vertical maneuver. Dive is the extreme nose down vertical attitude with increased speed and the descent rate. When the aircraft is on the lower half of the loop, the maneuver is called the pull up, where L is greater than the W. So if your aircraft is here and it is moving like this, this is called pull up. And if it is here like this, it is called the pull down or push over. In this, L is greater than the weight. When aircraft is on the upper half of the loop, here, this is the upper half of the loop, this is the radius R. So the maneuver is called the pull down or the push over. In this case, L is less than W, here L is greater than W. The pull down aircraft is inverted flight situation. In this climb angle, gamma is varying constantly. Question number 13, illustrate the pull up and the pull down maneuver flight with sketch. So here, if you can see, this is the pull up, this is the pull down or push over. Variation of load factor with respect to the pitch rate, as and when you are moving up and up, different load factors will change. In turn, no force other than the human weight is felt, while in the vertical maneuver, a centripetal acceleration is felt. In extreme case, human to pass out. Hence, vertical maneuver is limited to human strength, not aircraft strength. Structure can sustain load factor up to 2 to 30, but human can take only maximum 6. And how these things are happening? By the help of this diagram, we can see that during the takeoff, the stick is like this, straight. As and when you are pulling, it is pulling it towards the pilot. As and when you reach to the certain height, again the stick is come to the cruise straight. In the climb, initially for the some distance, you have to make nose up. So this is your diagram which shows how these things are performed. Next question. Consider an acrobatic aircraft with a mass of 1500 kg diving with a velocity of 100 knots. If the aircraft pulls out of the dive with a radius of 150 meter, determine the load factor. So in this, mass is equal to, so here mass is equal to 1500 kg, velocity v is equal to 100 knot, with a radius r is equal to 150 meter, determine the load factor. So find out the load factor. So we know the equation that load factor n is equal to v square by rg plus 1. So here v square is equal to 100 into 0.5144 square divided by r is equal to 150, 9.81 plus 1. You will get here n is equal to 2.8. Next is the question number B. If the maximum allowable load factor is 6, determine the minimum radius for a pull out of the dive. So from dive, again it is pull out if the load factor is 6. So we know that R minimum is equal to V square by G and max minus 1. V is equal to 100 into 0.514 square divided by 9.8 and N is equal to 6 minus 1. So 54 meter is the radius. This is the minimum radius of this aircraft which it can fly. So this is the solution for the problem, that your aircraft should turn with a radius of 54 meters. Name the chart used for the flight operations. We know that diagram of variation of aircraft lift coefficient versus Mach number, that is the first chart, CL versus M. Diagram of variation of airspeed versus altitude, V and H. Another diagram of variation of center of gravity versus aircraft weight. Diagram of variation of load factor versus speed, that is called the VN diagram. So in this we will be discussing what is the VN diagram and how it is important. So discuss the VN diagram of the airplane and show all with sketch. So we can see here that VN diagram, the envelope demonstrates the variation of the allowable load factor versus airspeed. So in this is the load factor in this direction N, and in this direction we have the V, speed. In other words, it depicts the aircraft limit load factor as a function of the airspeed. So limit load factor as a function of velocity. Allowable load factor is a function of strength of the aircraft. Producible load factor is a function of engine thrust and the power. So allowable load factor is by its strength of the structure, and producible load factor is from the engine thrust. Here we have the line. This line from here to here is a stall zone here. This is the aerodynamic And here also stall zone, aerodynamic. This is the structural failure. This is also structural failure. This is also at the, this is the negative, this is the positive. So positive is more. So if this is the 5, this may be the -2. And here we have the corner speed here. This is the speed where the structural and the aerodynamics should meet each other. And this is the your stall speed. Below this aircraft should not go, otherwise it cannot fly the aircraft. So the VG diagram and explain. So here we have the VG diagram. In this, VS for 1G is 200 knot at 3000 feet. VS increases with altitude due to the density reduction. As the density is decreasing, your VS will increase. Beyond 740 knot and above 6.5 G, and below -2.5 G, structural airframe damage may happen. So stay well within this limit. VNE is a never exceed speed. Beyond that, structural damage may take place. So this is the summary of this thing. This is the best zone where we have to fly the aircraft. I am just putting by this green. This is the zone when we have to flying envelope. This is the zone where we have to fly as per the different condition. This is called the VG diagram. Question number 15. Discuss the factor affecting the aircraft strength. So answer is, factors which are affecting the airplane strength are gross weight, that is the W, aircraft configuration, that it is fuel tank, missiles, etc. Symmetry of the loading, how the loads are distributed, and applicable altitude. At what altitude your aircraft is flying, that is also very, very important. In next lecture, we will be discussing about discussion on the question bank solution, safety requirement, takeoff and the landing performance. These are the references: Anderson J.D. Jr. Aircraft Performance and Design, International Edition, McGraw-Hill's, first edition, 1999. SL by ME, Aircraft Performance, Theory and Practice, AIA Education Series, AIA. Any questions, you are welcome to ask. My email ID is yddwivedi@gmail.com. Please do like and subscribe this channel. Do not forget to hit the bell icon. Please do that. I will be very grateful. Please do comment. If you feel any problem, it will be my pleasure to reply. Till then, goodbye and thank you very much for joining my session.
Like, share and subscribe. Hit the bell icon for more updates.